In this video, we will continue our investigation into the comparison and limit comparison tests. So as a reminder, the typical question we are now going to be asked is, given a series, determine whether it converges or diverges. Now note, for both the comparison or the limit comparison test, you need to be dealing with series that have all positive terms. So that's very important. But assuming all those terms are positive, for the comparison test, we know if we have this inequality, when the bigger quantity converges, so does the smaller. Additionally, when the smaller thing diverges, so does the bigger thing. Now, if you want to use a comparison test, that is, it looks like something comparable to a p-series or geometric series, but you cannot get the inequalities to work out. In that case, we move on to the limit comparison test. That's intuition. When the comparison test does not apply, but you would like to use it, move on to the limit comparison test. In this case, you take your two series and you look at the a sub n and the b sub n. You take the limit of their ratio. If you get back a number L which is positive and finite, then both of the series will converge or both of them will diverge. So let's determine if the given series converges or diverges. So we're dealing with the natural log of n over n. Now, based upon the form of this sequence we are summing up, we would like to somehow compare with either a geometric or a p-series. And my observation is, because of just the n in the bottom, could I somehow compare this with a p-series, specifically the p-series 1 over n? And the question becomes, when will natural log of n be, larger than 1? Well, most of the time. So this is going to be bigger than or equal to 1 over n, which is bigger than 0. Now this won't always be true. For example, if n equals 1, the natural log of n is 0. But in terms of when the natural log of n is bigger than 1, that would happen when n is bigger than e. So n bigger than or equal to, let's just say, 3 would work. And that's all we need. We need the inequality to eventually be true from some point onward. Now that we have the inequality, the comparison here, which is the hard part, we can immediately apply the comparison test. If the smaller quantity diverges, so does anything larger. So since the sum from n equals 1 to infinity of 1 over n diverges, the reason it diverges is it's a p-series with p equals 1. The comparison test implies that the series we are interested in, the sum from n equals 1 to infinity of the natural log n over n, also diverges. All right, so let's consider a second example. The sum from n equals 1 to infinity of 2 to the n over n factorial. Now, if we think about using the comparison or limit comparison test, we typically want to compare with p-series, geometric series. And here the comparison looks awfully difficult with the factorial. And the power as well may indicate a geometric series. But it turns out that if we have something of this form, something that involves both powers and or factorials. So if powers and or factorials are present, that's an indication that we might want to try something called the ratio test. So let's state a new test and see how it works in this scenario. The ratio test tells us the following. So once again, we need to have a series with positive terms. And for the ratio test, what we'll do is we'll take the limit as n goes to infinity of an plus 1 over an. Because the series has positive terms, the value we get back rho is going to be a quantity bigger than or equal to 0. So if the quantity is less than 1, the conclusion is that the series converges. If the quantity is bigger than 1, the series diverges. And if it's in the middle there, p rho equals 1, we say that the test is inconclusive. That is, we have no idea what happens. It might converge, it might diverge, but the test does not tell us either way. So let's go ahead and see if we can apply this ratio test. And once again, the intuition is when we have something involving powers and or factorials. So this is the ideal candidate. We will try the ratio test. So a sub n is what we are summing up. 2 to the n over n factorial. So for the ratio test, we need the limit as n goes to infinity of an plus 1 divided by a sub n. So this is the limit as n goes to infinity. And to form a sub n plus 1, what we do is we take a sub n, so we think whatever you plug in for n, you need to put into each of these boxes. So you take your a sub n, and in each of these 3 boxes we place an n plus 1. So 2 to the n plus 1 divided by n plus 1 factorial. And then algebraically, because this is going to be a very common technique, dividing by the fraction a sub n is equivalent to just multiplying by its reciprocal. So instead of writing a fraction over a fraction, we're going to multiply by that reciprocal. So n factorial divided by 2 to the n. And now we're going to make any obvious simplifications. So if we compare together the 2 to the n and 2 to the n plus 1. So the 2 to the n in the bottom cancels off the n in the top. So we're left simply with a 2. Another observation that's going to be very useful is recall n factorial is really n times n minus 1 times dot dot dot. We multiply it by every positive integer less than it. So if it's n plus 1 factorial, would be n plus 1 times n minus 1, all the way down to, once again, 3 times 2 times 1. So by comparison, this n times n minus 1 times dot 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 all the way to 3 times 2 times 1 is n factorial. So n plus 1 factorial is really equal to n plus 1 times n factorial. And this is going to be a very useful observation, not only in this video, but throughout the remainder of this chapter. So if we look at the n factorial over n plus 1 factorial, so that's really n factorial over n plus 1 times n factorial, which is simply 1 over n plus 1. So in terms of our algebraic simplifications, a 2 remains in the top and n plus 1 in the bottom. And the value of this limit is 0. And note that the algebraic manipulations that we have used here will be very common techniques. Instead of dividing by the a sub n, which is typically a fraction, we multiply by its reciprocal, and then we simplify algebraically using properties of exponents, and here we've also very conveniently used properties of factorials. So now our conclusion. The value of 0 that we have, just to make the connection above, is rho. And since this value of rho is less than 1, what we know is that the sum from n equals 1 to infinity of 2 to the n over n factorial converges by, and I'm going to write RT for the ratio test.